All right, recorded is rolling. So it is Thursday, January 12th. So we're a few minutes into class because we did a slinky review, stretches across the room, did some longitudinal wave, some longitudinal pulse across the room. We did like a transverse wave for count wavelengths. So you guys saw that. Let's look at a really famous case of something called resonant frequency. Let's switch my screen over here and come on here.
My name's Chase and I live in California, and I'm gonna try to break this wine glass by only my voice.
What you guys just saw was called resonant frequency. A lot of materials will have some associated resonant frequency, materials and structures. You guys know every there's some speed of sound. Well, it's different for air than it would be in the glass, but let's say you knew the speed of sound inside the glass, which is probably a little bit faster than it is in the air. Right? And that glass has some circumference, right? So there's some if you hit a note that has a wavelength that matches the circumference of that glass, right? And you keep pumping in that energy, right? Then it can cause that glass to shatter. It's resonant frequency. Right, you guys know speed is equal to wavelength times frequency. So if you know the speed of sound in the glass, you have the speed. And then the note that he was singing happened to match the resonant frequency, right? So you have to know the frequency of that note, okay? And then the wavelength would go around the circumference of that glass. Right? Now, some of this is kind of related to who in here is in ROTC? Who's in ROTC? Yeah, some of you guys? Right? So you guys learned to march and step, like left, right, left, right. Right? But there is one place where maybe you're told specifically to not march and step. You're told break step before you go over the over what? Might be crochet. Maybe how about a bridge, right? A bridge, right? Because do you guys think that a bridge structure might have a resonant frequency just like that glass, right? And if you hit that, and then right, so suppose that resonant frequency is like some multiple of like left, right, left, right. Do you think that could take down the whole bridge? Right. That's happened before. Troops marching across the bridge. What's going on here? Is my screen frozen? The screen's frozen. I'm sorry, guys. Let me pause this recording. All right, recording is resumed. Oh, hold on. Recording's resumed. Okay, we're good. All right, Tacoma Narrows Bridge. So we're going back to 1940. 1940. So this thing opens in July, and what's this? Something about a collapse in November. So it's open a few months. Let's take a look at this thing. So they build this bridge, and they do notice that it kind of like bounces up and down, which it wasn't really supposed to, but like, okay. So had engineers keep an eye on it, and it's not really cracking apart, so it looks like it's probably gonna be okay. Until one day, this happens. You see an engineer out there walking along the nodal line. Here's his car parked out there. Right. So a few things about this. One is that there's some kind of energy making this thing move. Like it's not just moving spontaneously, right? So where's the energy coming from, do you think? Like, what's driving that motion? No cars going over it right now. Yeah. Okay, yeah, and then okay, so maybe there's energy transfer from the cables, and then where's that energy coming from? What do you think's blowing across? Wind. Yeah. So there's a huge crosswind. There's a strong crosswind there. Okay, and I'll show you guys after this video. We're not accounting for that. All right, so yeah, huge crosswind hits. If you count the time period it takes to oscillate back and forth, I think it's like pretty close to 5 seconds. So I think someone would say like 5 seconds. Okay. Guys, 5 second time period. What's the frequency of that motion then in hertz? What's the frequency in hertz? What's the relationship between frequency and time period? Just reciprocal, like 1 over, right? Because what's 1 over 5 seconds? Is that 0.2 hertz? So that could be the resonant frequency of that structure right there. It's like 0.2 hertz, right? And the wind's just driving energy into it, pumping energy to it. So 0.2 hertz resonant frequency. Right. Now we're but by the way, that guy got off in time, so he did not die in this collapse. So it's been all right. Yeah, so that happens. Now, you guys, you see the columns look okay, right? Like, I don't see a problem with the columns. It's just the road itself. Oh, I was going to ask you guys, what do you think that road was made out of? Like concrete and steel? Are you guys thinking concrete and steel? Yeah, you are right. Concrete and steel. So they went back and just rebuilt it, made one tiny change in the way they built it, and ended up being all right after they rebuilt it. So what did they do? Like, what went wrong, and what did they learn in terms of engineering from this, and how they go back and build this right? So they were thinking when they were designing building this thing that, well, there's going to be a bunch of cars going across the top, and cars weigh a lot. So what's the best way to carry a bunch of weight? Well, it's to have a bunch of vertically oriented support structure. Okay. So I put in all these vertical girders, which maybe in isolation could have been a good idea, but in the real world, there's all kinds of other forces that they were accounting for, thinking about, like, oh, like a really strong horizontal crosswind. Oh boy, horizontal forces. This is not going to be good at carrying because everything's like vertically oriented. And so after this thing collapsed, they went back to rebuild it. What do you think they did to fix this? Instead of a bunch of vertical girders, instead you use what kind of system? You guys thinking a truss system? Okay, that's what you guys thinking? Truss? Right. So now that you have these bars that are off on angles, so now this can also carry some horizontal loads too, in addition to vertical, and then it ended up being all right. Okay. Do you guys remember last semester we were saying something's at rest? That's a type of equilibrium. The forces have to sum to 0. So if any of you do engineering classes one day, you might do something like design truss structures. And then one thing you do there is you can pick any point in the structure and the forces have to sum to 0. Okay? So, and then you can figure out what's the compression or tension in each of these bits. Okay? And suppose, just pretty straightforward, maybe this whole thing's trying to like bend this way, for example. Okay. And if that's true, maybe everything on the top is kind of in compression and everything in the bottom is kind of in tension, right? Might get you started there, but the forces have to sum to 0 at each point in each direction, each axis. All right, so here it is, the Tacoma Narrows. Right, resonant frequency. Right, so I gave you guys this half page here, Doppler puzzles. You guys remember the other day, brought out the Doppler ball, was swinging that around. Right, so we're going to go through all these Doppler puzzles. Here's Doppler effect. Okay. So I've got a car in motion and I've got an observer out here. Okay. And if you're inside the car versus if you're out on the sidewalk, you hear different things. Right? This guy on the sidewalk, as the car passes him, that's like, is that what that would be? Right? Okay, so this guy observes different frequencies, frequency observed. Right? Now, if the car's parked, it would match the sports frequency, right? So the car horn might be like, beep, beep, right? That's this, but what's this guy here? Right? Right, well, it depends on the motions of these objects. Motion of the observer, motion of the source. Right? And here's the speed of sound, a couple places. And so we're going to navigate this Doppler formula for a bunch of different scenarios. There's a little bit of logic with these puzzles because you have to figure out, well, do a plus or a minus, right? Plus or minus option. So we've got a car traveling at so many meters per second. Oh, you guys know everybody's paper has different numbers, right? So your numbers are different than my numbers, okay? But we all have the same questions, right? Just different numbers. Okay? And this car horn is so many hertz frequency, right? You guys know frequency is think of it like musical notes, like beep beep. There's some associated frequency in hertz. So the first scenario, let's just have these two guys standing on the sidewalk. They're just standing, the car's like going past them. Okay? But oh look, it's going away from person A and towards person B, sort of. Okay? So first question, what frequency of the car horn is someone here inside the car? Well, if you're traveling along with the car, right, with a pocket of air inside the car, everything's moving together, would beeping the horn sound to you exactly like if you were parked? I think it would, right? If you're parked, you hit beep beep. If you're traveling along with the car, you hear beep beep. So whatever the car horn frequency is, just can you guys just copy paste that number right here? Right. So I would write 440 for 440 hertz. Do that. You guys do that. So there you go. That's everybody's first answer. Right. I'll pick this up at the end of class. So as long as you guys are following along, then you get some points today. Okay. Next couple of questions are, what is each of these guys here? Okay. So we got person A, the car is going away from, and person B, the car is headed towards. Okay. Since person A is lined up right here, does person A hear a high or a low frequency? Yeah, low frequency, right? Because the car's going away, right? So somehow we have to navigate this Doppler shift formula so that the observed frequency is less than the source frequency, like a lower number. Like if this number is 440, this might be like 400 or something, right? Or like 390 or something like that. So let's figure that out. I'll go frequency observed is equal to the source frequency multiplied by a big old ratio. We got speed of sound plus or minus the speed of the observer, all divided by speed of sound plus or minus the speed of the source. Okay. The source frequency, I gave you guys, that's just the car horn. Now I'm just going to make up a crazy number, and that's probably not your number. So I'm just going to call it 400 hertz. Okay, so that's just my car horn. Okay, everybody found their car horn, right? That's okay, that's this number right here. Sure, car horn frequency. Okay. The speed of sound. I think everybody's paper is the same for this one. It's just like 343 meters per second. Now that depends on atmospheric pressure and temperature. So if it's 1 atmosphere down here at sea level and it's room temperature, that's like a number you can use for the speed of sound. Okay. Like from my voice to your ears right now is probably about that speed. Okay. Now, since each of those guys is just standing around, what's the speed of the observer? Just be 0. Okay, so this is just 0 meters per second. It's just standing there. Okay. Now the car's in motion. Car's in motion with some speed. And I told you guys how fast the car is moving. That's that first box. So many meters per second. Is that? Okay. So I'm gonna just make up a number just off the cuff here. How about 19 meters per second? Just make something crazy up. So no, you guys aren't going to do that unless it says on your paper, but I don't think it does. There's okay. Now here's where the logic kicks in. So for person A, now person A, the car is going away from. Should you add or subtract down here? The numerator doesn't really matter because it's just plus 0 anyway, right? But denominator, should you add or subtract the speed of the car? Well, what would happen if you subtracted? Because if you subtracted, that would make the denominator what? Big or small? Small. And then you have 343 divided by something less than 343, which means this ratio would be what? More than or less than 1? More than 1, right? Yeah, so for example, 343 over 340. Okay. See how if you divide by smaller numbers, it blows up more than 1? Okay. And then if you started with the frequency and multiply by something more than 1, would that show an increased or decreased observed frequency? That'd be increased, right? Because it'd be more than 400 hertz. That'd be like that'd be a higher pitch. That's like the opposite of what we want to do, right? Okay. So let's go back to this. So do you want to add or subtract here? It's got to be add. It's got to be add. Okay. For person A, it is right. For person A, who the car is going away from. Okay. So I'm gonna go at the car horn. Just my number is probably different than your number. Right? All multiply by. Now this is just 343. All divided by, and then this plus this 343 plus the speed of the car. Okay. And if you do it right, you should get an observed frequency for person A that's less than the source frequency. Like with my numbers, I'm getting this many hertz. Okay. Now don't write 379. that's a freak coincidence it happens to be, but I don't think it is. You're gonna write some number that's less than the car horn frequency. For same process, just different numbers. Okay, you guys get that? Get that? Huh?
Can you show us what you're doing time later?
Okay. Yeah. So I check this number here. Is that number there? Multiply by, or you just open a parenthesis. Okay. Speed of sound, plus zero, just ignore that. Just plus zero just doesn't even matter, right? Okay. So then divide by, fraction is divide. Okay. Then group this in parentheses. It's really important you group this in parentheses. You have group them, divide by open parentheses. 343 meters per second for the speed of sound, plus the speed of the car. So plus down here. Yeah. All right. And you get, yeah.
When do you know when to add and when to subtract?
All right. So my go-to method for should you add or subtract is just logic of should you ultimately hear a higher or lower pitch. There's another perspective too, but here, let's start with this one. So from this guy's point of view, person A, the fact that the car is going away should be like a lower pitch. It'd be like, so lower pitch. That's a low pitch. Okay. So how do you get a low pitch? Well, that's like a small number of hertz in terms of the frequency. We need the observed frequency to be less than the source frequency. 379 is less than 400 hertz. Well, how do you get that? Well, you get that by taking the source frequency and multiplying by a ratio that's less than 1, at like 0.9 something, right? Has to be less than 1. Well, how do you get that? Well, the denominator has to be bigger than the numerator, or the numerator has to be less than the denominator. Well, how do you get that? Well, you get that by adding on the bottom. Okay, if you add on the bottom, makes the denominator big, makes the fraction small, makes the observed frequency less than the source frequency. Okay. All right. Next question. How about person B? Now, person B, looks like we got all the same numbers, but it's gonna be different because the car's headed towards this person. So now that should sound like a high frequency, right? So he got a high frequency. So the frequency observed for person B is the source frequency. Okay, now you guys aren't writing 400 hertz. That's just my number. Multiplied by the speed of sound, 343 meters per second. You can leave plus 0 on top because he's just standing there, so that didn't change. All divided by, right, and then group this in parentheses in the denominator. We have 343 meters per second. Now the speed of the car is well, I used 19 meters per second before, so I'll just use that again. Right. Okay, now here's where the logic kicks in. The fact that this car is headed towards person B, this person B needs to hear a high pitch, which needs to be greater than, in my case, 400 hertz, maybe 410 or 420 or 430. How do you get that? Do you get that by adding or subtracting on the bottom? Subtracting. Has to be minus. Okay. Subtracting on the bottom makes the denominator small, makes this overall fraction bigger, like bigger than 1 in this case. Multiply by the source frequency, you get something bigger than the original source frequency, which would be a high pitch, which is exactly what we're looking for. Okay. Let's go. And then very simply, you can just flip in a negative sign where the positive used to be. I'm looking at this many hertz. Yeah, that looks about right. So it should be bigger than the source frequency. Right? Okay, you guys okay with that? So everybody got the first 3 boxes? So everybody has the first 3 boxes filled out, right? Okay, everybody good? All right. Scenario number 2. Got a new scenario. Got the car traveling at the same speed as before and has the exact same horn as before. Okay, so same speed, same horn frequency. Okay. But now we got person B running towards the car. Hey, running towards the car. Is that going to increase or decrease the perceived frequency? If you're running towards it, it's going to increase it, right? It's going to increase, right? You're running towards the car. If the car heads towards you, it's going to increase it. If you run towards the car, it's going to increase it even more. So it's going to increase twice. Once because the car is headed towards the guy, and the other time because he's headed towards the car. So both those effects combined together to really increase it, right? Hey, do you guys think that this last box is going to be some number of hertz that's even greater than the previous box? I think it will be. Okay. Let's try. Let's go. Frequency. Observe for person B for that last box. It's going to be the source frequency. So whatever your car horn is, multiplied by big old ratio. Let's put in the speed of sound right there and right there. Okay. We know the speed of the car is whatever it is on your paper, which is different for everybody. And we know the speed of the person. Let's make something up. How about this meters per second for the guy running? Okay, it's pretty fast, but let's just go with it. Right. Well, I remember the last one where the car was headed towards the guy where you subtracted on the bottom. Is that still going to be the case? Minus on the bottom? Yeah, so going to be minus the bottom. Okay. So that's going to cause the frequency to go up already. Right. How about the numerator? The guy running towards the car. Should you say plus or minus on top? Show of hands. How many of you say it's plus on top? Plus on top. Yeah, plus on top, right? Right. Because if you add on top, isn't that going to blow up the numerator larger, which makes the overall fraction bigger, which is exactly what we're looking for, right? Because the fact of running towards the car would also cause the pitch to go up, right? Right. Do you guys see how these signs are opposite from each other? Right, 1 plus 1 minus. Right. So some textbooks or teachers have a little bit different perspective on Doppler, right? So they might say something like this. They might say, well, the fact that they're traveling in opposite directions, the car's going to the right, and the person's running towards the left, is also a hint that these signs have to be opposite of each other. Okay, so it's a little bit different way of thinking of it. Okay. So plug this in and see what happens. Got the source frequency multiplied by speed of sound plus the speed of the person. Close parenthesis, all divided by open parenthesis. Speed of sound minus the speed of the car. And the observed frequency that you get should be the largest number you have on the entire front side of the page. Is that the biggest number you have on the entire front side of the page? Yeah, it needs to be, right? A little bit bigger than the previous box. Right. Is everybody good with the front side of the page paper? You guys good? All right, you guys ready to flip over and do some on the back? Scenario number 3. A car in neutral rolls off a hill of this given height. So I told you how tall this hill is. And it's blaring its horn while it's going down and across the bottom. Person D is running away at so many meters per second, trying to run away from this car. So when the car's at the bottom of the hill and rolling towards the person on this flat track at the bottom, down here in the valley, okay, what frequency does person D hear? Okay. So this is going to be a multi-step problem. I'll walk you guys through it. So as long as you guys follow the steps here. Okay. Do you guys think we need to calculate what is the speed of the car before we can do all the Doppler stuff? But the speed of the car, does that have to do something with the height of the hill? You guys think the taller the hill that rolls down, the faster it's going to be going? Ooh, does that sound like conservation of energy from first semester? Is what kind of energy does the car have at the top of the hill? Potential energy, right? And what kind of energy at the bottom? Kinetic? Okay, so we need to solve a side problem first, which is conservation of energy to get the speed of the car at the bottom. Then what we're going to do is hold on to that number, and we'll go back to Doppler, and then we can actually solve this question. Okay. So first part, this is part 1. Sum of energy initial equals sum of energy final. Do you guys remember what is the formula for potential energy? MGH. You guys remember MGH? Right. There's the height of the hill. Here's the gravity field of the planet. Here's the mass of the car. You guys said it's kinetic at the bottom, right? Energy, motion, kinetic. Do you guys remember a formula for kinetic? 1/2 mv squared. Guess what that? Right. Oh, v. Hey, that's what we want to find. I want to find the v. Mass of the car cancels. Cross multiply 2, take square root. So v squared is 2gh. So the speed of the car is square root 2gh. Okay, so let's figure out what is the speed of the car at the bottom of the hill. Let's use 9.8 meters per second squared for g. And the height of the hill, here, I'm just gonna make up a crazy number, which, all right. How about this many meters? Right, so that's the height of my hill, which might be different than the height of your hill. In fact, it probably is different than the height of your hill. Okay, so I'm just making stuff up. So you can do this to get the speed of the car at the bottom of the hill. This is assuming no frictional losses. Kind of a maximum boundary case, but it's all right, upper boundary. All right, now that's not the number that goes in the box, but jot that number down somewhere, the speed of the car at the bottom. Okay, that's part 1 of 2. Right? This is like a 2-part problem. We just finished part 1. We're gonna switch over and actually do the Doppler part now. Okay, so are you guys good on the speed of the car? Everybody figure out the speed of the car? All right, all right. Now let's do the Doppler bit. So the observed frequency for a person D is the source frequency, which is however many hertz the part horn beeping, multiplied by big old ratio. Gonna do speed of sound. Now, both the observer and the source are in motion. I know that this guy's running away at like so many meters per second. That's straight off the paper. But it's right there. And the car speed, well, that's what we just did. Okay. The car rolling down a hill of some height. And right there, goes right here. Got that, right? Okay. All right, you guys good so far? All right. All right. Now, last bit of logic before we break out the calculator. We got to figure out, is it plus or minus on top and on bottom? Okay. Remember, this guy's running away from the car, but the car's headed towards him. I think those are competing effects, right? The fact that he's running away from the car would tend to make the frequency lower, but the fact the car is headed towards him would tend to make the frequency higher, right? I think the car's going to win because the car is going faster than he's running. So, do you want to add or subtract on the top? Subtract. Right? Because the fact that he's running away would tend to lower the frequency, and that would be consistent with that, making the numerator smaller. Okay. Should you add or subtract on the bottom? Also subtract, yeah. Right? Because that would make the denominator smaller, which blows up the fraction bigger, which tends to increase the frequency. Right? Or, like I was saying a few minutes ago, the fact that they're both going in the same direction, right? So the fact that the guy's going to the right and the car's also going to the right is an indication that you need the same sign, right? It's a little bit different way to think of it, but it also works. All right, let's pop this in the calculator and get some number of hertz. Right. Let's do a prediction. I think I should look for something that's larger than 400 hertz, larger than the car horn itself. Okay, that's it. And it is. All right, and that's working out for you guys too, for your paper? Working out? All right, are we good? All right, last scenario. Scenario number 4. So same car, same horn, same frequency it's been for this entire paper. Is now equipped with rocket boosters. Ooh, look at that. Great balls of fire. 600 meters per second. Whoa. Screaming through the streets. All the way. Towards person G, who's running away, probably unsuccessfully. And person E is just standing here watching this whole thing happen. All right. You know what? I got my own side question before we get going too far. Guys, is that car going faster than the speed of what? Sound. Faster speed of sound. Is that a supersonic car? Let's get a Mach number. Let's get a Mach number. You guys remember how to get a Mach number? Okay. This is Mach what? Let's go the speed of the car compared to the speed of sound. Is that like Mach 1.75? That's almost Mach 2, right? That's getting up there, right? That's almost twice the speed of sound, right? Okay. Hold on to that idea. That might be relevant in a few minutes. Okay. So, 3 questions. First question, what frequency does someone hear inside the car? Well, guys, if you're inside the car, are you traveling along with the car with a pocket of air that's also moving along with the car? Do you think you would still hear it as if it were parked? The exact same as the very first question on this entire paper? Right? I think so. I think take the car frequency, whatever the horn frequency is, and just copy paste it right here. Same frequency, right? Because there's a pocket of air traveling along with the car, right? Oh. Next question. What is person E here? Okay. Hey guys, person E, is this guy going to hear a very high or a very low frequency? Very low, right? Very low frequency. Because this car, right? Really screaming past really fast. So, see if you guys can set up the Doppler equation for low frequency. Now, if you want a very low frequency, should you add or subtract on bottom? Add. Because let's make the denominator huge, which makes the overall fraction very small, which is going to show a lowered frequency. All right, so let's put it all together. All right, I guess we're on. Of course, as always, my numbers are different than your numbers, but you get something kind of like that. Same structure formula. Yeah. Okay, so you're on to the next one. All right, you guys ready for the last one? Last one? All right. Yeah, so you're right. Person G, the car headed towards. If you take this formula at face value and you plug in a negative sign there, you do end up getting a negative value. Can you have a negative frequency? No, there's something fishy going on with this last one, right? This last one might be kind of a trick question, sort of. What's the weird trick going on with this, and how can you get an answer that's not a negative frequency for the last question? What is this guy here? Car heads towards him. I'm gonna pause this video and let you guys think about this. Pause recording. All right, recording's resumed. All right, so Evan said something about a sonic boom. Wait a minute. If you hear a sonic boom, that all the sound waves have to reach you for you to hear the sonic boom, right? And they will reach all at once. It'd be like that cone situation, right? Yeah, that's fine. Something like this, right? Hey, suppose there's like a guy right here. There's like a parachuter going like, supersonic plane. Okay. So he's like right here. Does he even hear the plane yet? No, because none of the sound waves reach him. Right? Isn't the plane like out racing the very sound waves it's sending out into the world? Isn't that exactly what we're dealing with here? So what does this guy hear? Nothing. That's the answer. No sound. No sound. Scratch out Earth. There's no Earth going on. There's nothing. There's no sound. Okay. It's completely silent. All right, so server had every single box filled out on that page. Okay, once you do, pop that in the grade tray, and I will get points in the book for you. We have a few minutes left, so I'm gonna stop recording and flip over and show you guys some fun demos. What we do.